Problem number 2. We have another system to solve. X prime equals negative 4x plus 8y plus 8z. Y prime equals negative 4x plus 4y plus 2z. And z prime equals 2z. So we can put this in a matrix form if we just look at the components. We get x prime, y prime. I'll use a different color. X prime, y prime, z prime, which we'll call x prime, equals negative 4, 8, 8, negative 4, 4, 2, and 0, 0, 2 times x, y, z. And we'll define this to be our matrix A. So we get the equation x prime equals A, x. So that means this equals x. And now we just look at the determinant of A minus lambda I to find our eigenvalues. So A minus lambda I equals negative 4 minus lambda, negative 4, 0. 8, 4 minus lambda, 0. And then 8, 2, and 2 minus lambda. And the determinant of this equals if we expand along the bottom this way, then we get 0 times this submatrix. It doesn't really matter what it is. Sorry, the determinant of that submatrix, or minus 0 times the determinant of this submatrix plus 2 minus lambda times the determinant of, sorry, I'm erasing part of this. So this determinant, so negative 4 minus lambda, negative 4, 8, and negative 4 minus lambda. And, sorry, this is positive 4 minus lambda here. And since these are just 0, this will just be 2 minus lambda times negative 4 minus lambda, 4 minus lambda, minus negative 4 times 8. So this will simplify to negative 16 plus lambda squared plus 32, or 2 minus lambda times lambda squared plus 16. So setting this equal to 0, since this whole thing is equal to 0, gives us lambda 1 equals 2. And then setting this equal to 0 gives us lambda 2 and 3 equaling plus or minus 4i. So we can deal with this real eigenvalue first. We look at a minus 2i, which is going to be negative 6, 8, 8, negative 4, 2, 2, and 0, 0, 0. If we're looking for a v1 that equals a, b, c, this is just a matter of satisfying this equation. And once if you get this into an augmented matrix form, and you row reduce this, you get 1, 0, 0, 0, 1, 1, and 0, 0, 0. And this tells us that a equals 0, and then b plus c equals 0. So a equals 0, b equals negative c, and c equals c. That means v1 equals 0, negative c, c. If we let c equal 1, then we get b1 equals 0, negative 1, 1. And that gives us our first solution. This is going to be called x1, e to the 2t times 0, negative 1, 1. So now we'll look at our complex eigenvalues, and as we predicted, they come in a pair, plus or minus 4i. These are conjugates of each other. So we just need to look at lambda equals 4i, so we pick the positive one, and then we consider a minus 4i times identity matrix. That's going to equal negative 4 minus 4i, negative 4, 0, 8, 4 minus 4i, 0, and 8, 2, 2 minus 2i. And we want to find a complex eigenvector, w, and we'll say w has components d, e, f, and w is going to satisfy this equation. So this gives us the augmented matrix. And if we start by taking R3, dividing by 2 minus 2i, we'll get 1, 0, 0, 1 on the bottom. And then this will clear these two entries in the column. And I won't show the exact procedure for that, but that's just how this row reduction works. So that tells us right away that our third component of the vector is going to be 0. Now we just need to find the first and second components. We can do that by just both of these will give us the same result. So what we can do is we can just look at this. Let's divide the second row by negative 4. So that gives us 1, negative 1 plus I. Yeah, and 0. So let's look at what this tells us. This tells us, if we just look at this row specifically, it tells us the first component d plus negative 1 plus I times e equals 0 and f equals 0. That means d equals subtract this over, it is 1 minus I times e, and e equals e, and f equals 0. Same thing will happen if we use this top row, but bottom row is a little simpler to use. So that means our eigenvector, our complex eigenvector w equals 1 minus I e, and 0. If we set e to be 1, that means w equals 1 minus I, 1, 0. So now we'll find our complex solution, which equals e to the lambda t times w, or e to the 4i t times 1 minus I, 1, 0. We can use Euler's formula to expand this out to cosine 4t plus I sine 4t. And then we can convert this into a real part, 1, 1, 0, plus I times negative 1, 0, 0. Now we can just multiply these two parts together. So if we multiply this by this, we get cosine 4t times 1, 1, 0. If we multiply these two together, we get I squared, or negative 1 sine 4t times negative 1, 0, 0. And then we can multiply, this I sine 4t by this vector. So we get I sine 4t times 1, 1, 0. And we can multiply this cosine 4t by this I negative 1, 0, 0. This will also have an I, so we can just factor the I out. So we get cosine 4t times negative 1, 0, 0. So you can see right here, this is the real part of the solution. Sorry. And this is the imaginary part. So the real part we can write as cosine 4t plus sine 4t, just multiplying these components. Cosine 4t minus 0 sine 4t, and then last component is just 0. And then we have sine 4t minus cosine 4t, and we have sine 4t and 0. So this real part is going to be one solution, so we'll call this x2. x2 is going to be cosine 4t plus sine 4t cosine 4t and 0. And then this imaginary part, x3, is going to equal sine 4t minus cosine 4t sine 4t and 0. So now combining what we have, we get x of t equals c1 times x1, where x1 was e to the 2t times 0, negative 1, 1. Plus c2 times x2 plus c3 times x3 and we can split this up to get our x, y, and z back. So x was equal to c1, actually not even, there's 0 for the c1 component. So it's just going to be c2 times cosine 4t plus sine 4t plus c3 times sine 4t minus cosine 4t. And then y is going to be negative c1 e to the 2t plus c2 cosine 4t plus c3 sine 4t. And then z is going to equal c1 e to the 2t. These are the solutions.